Welcome, everyone, to IEEE Magnetic Society's Santa Clara Valley chapter's webinar, What If All Memories Were Persistent by Tom Coughlin. Before I introduce the speaker to you, I would like to first remind you, please keep all your microphone muted. When you have a question, during the presentation, you may type in your question in the chat box. And at the end of the presentation, you can also raise your hand and we may enable you to video and a microphone so that you can ask your questions. Today's speaker, Tom Coughlin, he's the president of the Coughlin Associates. He has more than 40 years experience in the data storage industry with engineering and senior management positions. He's a consultant doing digital storage analyze and physical technology consultancy. They publish books and market and technology reports and puts on digital storage-oriented events. He's also a regular contributor for Forbes.com and M&E organization websites. Tom has been very active long-term IEEE Magnetic Societies. He's an IEEE fellow. He's the 2023 IEEE president-elect, and he served Region 6 as a past director and the past chair in the Santa Clara Valley section. He's also active with Advancing Storage and Information Technology and the Society for Motion Picture and Television Engineers. With that, I would like to turn the control of the screen to Tom. Tom, the floor is yours.
Hi there. Thanks for inviting me to talk. I'm going to talk to you today about changes coming in the design of computers, driven by the huge growth in demand and the ways that we move and we store information. So here's an outline of things to cover today. We'll talk a bit about some of the growth drivers for storage and memory and current memory environment. We'll talk about the evolution of computing and memory, things that are going on now. We'll talk about scaling issues with conventional memory technologies. We'll talk a bit about some of the particular non-volatile memories and then get into some potential changes in processor design, and finally, some summary. So data growth is exploding. IDC has projected a few years ago 175 zettabytes of data generated annually by 2025, and that's up from about, say, 80 zettabytes in 2021, for example. Now, most of this data comes from Internet of Things devices, sensors, cameras. It has the most value when it's processed real time. And that's going to increase the need to store and process data in the device or at the network edge close to the device so that you get low latencies. And probably only a few percent of this data is going to be stored long-term, or the results of the data is stored long-term. Now, greater use of artificial intelligence in devices at the network edge and also in data centers is also increasing memory requirements. In addition to the growth of data being processed, power consumption as well as latency and data rates are important considerations in future system design. And this leads us to look at the storage and memory technologies which will enable handling this data tsunami. So modern computing uses various volatile, that is, when the power goes off, the data goes away, as well as non-volatile memories. They keep the data even when the power goes off. Volatile memories include DRAM and dynamic random access memory, and SRAM, which is static random access memory, which is used for the main memory in computers and also high performance cache memory. Non-volatile memories include flash, which can be either the NOR or NAND variety, as well as emerging non-volatile memories such as magnetic random access memory or MRAM, resistive random access memory, RRAM, ferroelectric random access memory, or FRAM or FERAM, some people call it, and also phase change memory. New computer systems, particularly in large data centers, are moving away from traditional von Neumann type computer architectures where data moves back and forth from CPU to one with much less data movement. data centers are moving to what they call disaggregate traditional server components. That is to remove them from a server and actually create pools that should then be put together. And that includes the compute, memory, storage, and communications. And then they use software again to create what they call composable infrastructure. That is, it puts together with the software to run applications. That could be a virtual machine, it could be a container. There's a number of ways and approaches that people have in doing this. Slowing of the rate of semiconductor lithographic shrinking is leading to new computer system design. This includes, for instance, with it getting more and more expensive to make small lithographic features, chiplets, where I can use the high cost small lithographic features where that gives me the greatest advantage, and I can use more relaxed lithographic features for other components. And I combine them together, these little chiplets in a package to create customized computing packages. Embedded devices, such as system on chips or SoCs, are used in industrial applications, edge devices, consumer products, and Internet of Things applications. And they're needing more memory to run sophisticated applications such as machine learning trained inference engines. Now let's look at how new memory technologies are changing the way that data is stored and processed. In a von Neumann computer, like shown on the left, lots of energy and time are wasted moving data around. These energy and time issues can be addressed by moving from a von Neumann architecture to a memory-centric approach, as is illustrated on the right. So this opportunity has led to new, in that case, we see we have some direct connected memory like DRAM to the CPU, but then we have an interface that creates a pool of memory which can be shared. This opportunity has led to new protocols like CXL. CXL supports memory disaggregation. It allows you to remove some memory from behind the processor. It allows memory pooling and sharing to more efficiently use storage and memory to address new problem classes. And there's something called heterogeneous computing, which allows data to be processed by a variety of types of accelerators. And note that this memory-centric system includes a low latency DRAM connected directly to the CPU as near memory. You can see that up at the top. And what we may call far memory at the center of the diagram, which is labeled SCM memory. That stands for storage class memory. Since the far memory is shared, its data path to the CPU must be arbitrated. So there's a switch in there, and that adds latency, a little bit of latency. Thus, we have this term near and far. So there's a little bit higher latency for this far memory than there is for the near memory. Now, CXL is backed by a big consortium and will be a switched memory channel that enables pooling of non-heterogeneous memory with various latencies and data rates in storage boxes. CXL supports memory and accelerators for resource pooling and allocation. DDR channels, that's used in conventional working memory in computers. DRAM has, in a lot of computers, uses the DDR interface, will continue to be used for low latency memory, at least through DDR5. Beyond DDR5, options such as the Serial Open Memory Interface, OMI network, which is also now part of the CXL consortium, could provide more scalable near memory options should people need them. Now, an interesting thing about CXL, it's been developed over the last few years. Last year, we started seeing some components coming out of many companies that enable CXL. This year, by the end of this year, we expect that there's going to be some actual computing systems that will include CXL architecture, and there definitely are folks that are offering various services and expansions and specialized cases with CXL as well that are even available out there now. Now, in addition to these new hardware architectures, new software paradigms are needed with non-volatile memories. The new programming paradigm has been, or actually for several years now, has been guided by the Storage Networking Industry Association's NVM programming model. You can see a drawing of the basic concept here. It provides guidance on adding persistence in memories and even caches. Now, this model characterizes various types of access to persistent, that is non-volatile memory, including a persistent memory-aware kernel, a persistent memory-aware filing system, and direct access to a persistent memory from a file system, or ideally from an application. And some of these new technologies are beginning to allow that to happen. So let's talk about programs for scale conventional memory technologies. So various types of memory and storage are used in a modern computer. These different technologies can be seen as creating a hierarchy of storage and memory, with a little very fast and very expensive memory and registers at the very top, for example, and a little more but slower and less expensive memory in various cache levels down below. Now, this main memory is usually DRAM, which is somewhat less expensive than the SRAM caches. Slower and less expensive storage for large capacity are SSDs and hard disk drives. And SSDs, at least if you do apples to apples comparison, are about 5 to 10 times higher in cost per native capacity unit than hard disk drives. And these are the mass storage in most computers. Magnetic tape is used for very, very cold storage because of its high latency time to data, but very low cost for storing content. The actual cost for magnetic tapes right now on is less than a penny a gigabyte. I think it's somewhere around 4/10 of a gigabyte right now, 4/10 of a penny per gigabyte cost, for example. So it's the lowest low cost of storage that's out there today. Now there's another way of viewing the storage memory hierarchy where we compare the cost of storage and memory to performance as shown here. Now, these are log scales on the price per gigabyte versus the bandwidth. This is actually done by my colleague, Jim Handy. He and I do a report on emerging memories, and he's shown this chart, of course, many times. And often in a storage system, multiple types of memory and storage are combined together to provide the best combination of performance and price for the given application. However, many conventional memory technologies have scaling limits. Everything in this chart is normalized to SRAM's cost at 500 nanometers. And again, we have a vertical log axis here, and looking at the lithographic trends on the horizontal axis, going from large lithographies to very small lithographies on the right, on the left, very small lithographies on the right. So this chart is normalized to SRAM's cost at 500 nanometers. That's half a micron. It uses a log scale again because processes move exponentially. Every process mode is roughly 70% the size of the prior one, and costs move proportionately to that because of the amount of wafer space being used for the device. NOR flash memory has a problem after the 28 nanometer node, and that's why you see that red line there peeling off at about 28 nanometers. NOR flash is the non-volatile memory that the industry uses to store the code in microcontrollers, application-specific integrated circuits, and other system on chips, and it stops scaling at about 28 nanometers. This causes cost declines to cease. That's why that red line abruptly goes horizontal at about 28 nanometers. Now, according to papers presented at an IEEE conference over the last few years, the cell area, and thus the cost of SRAM cells, stopped shrinking at about 14 nanometers. Thus, SRAM cost reduction with die shrink stop at that point. SRAM also has several transistors per cell, while the emerging memory candidates you're going to talk about in a little bit here have a single transistor. For applications such as AI inference that need lots of memory, the emerging non-volatile memories can provide the same capacity in a small die space and thus cost less than the SRAM. We assume that this new tech wafer, a new persistent memory for the slide costs 5 times as much as NOR or SRAM. That's this black line here. As long as the new tech can move to processes past the NOR and SRAM, that is, go to smaller lithographies, become cheaper, and despite the higher wafer cost. That's why so many people have invested so much money to fund the research of these new non-volatile memories. The bottom line is that new memories are inevitable. They must gain acceptance for chips to continue to scale in price. To show what this means to chip sizes and cost, I'm going to present an animated graphic. This is a photograph of an Intel processor chip made on a 45 nanometer process. You can see two very different parts of this layout. The less regular part of the chip at the top is the logic, and the lower half with its very regular patterns is the SRAM used for the on-chip caches. In the past, the entire chip would scale with process shrinks, as illustrated here, as processes moved from node to node, from 45 to 32, 22, and finally 14 nanometers. The die's area, and thus the cost, would be half that of the prior generation. It follows a very nice scaling curve. Now, this assumes that the SRAM keeps pace with process technology, though, and this prior slide shows us that this doesn't happen at the 14 nanometer node. So we use that same chip again, keeping in mind that the top half is logic, which will scale in proportion to the process, and the bottom half is SRAM, which will scale less aggressively. You can see in this series that the top half of the chip gets pretty small towards the end and only accounts for about 20% of the total die at the smallest process node. Yet the SRAM doesn't scale, resulting in a pretty large chip. In fact, the die size trend starts to level off at the end. This black line only indicates the height. The area of the chip would be roughly equivalent to something like the scale of this figure, indicating a very significant difference between the size of the chip for these two in these two cases. The SRAM has caused the chip to be larger and more expensive, and this gives an opportunity for an emerging non-volatile memory technology to replace SRAM as this happens. Thus, NOR and SRAM scaling will stop, and emerging memory will take over as the embedded memory and system on chips. That emerging memory will be persistent. We will see emerging memory caches and registers as well, I believe, with persistence closer to the CPU or even within the CPU. That's going to include mixed memory speeds, SRAM versus emerging memories, for example. And mixing emerging memory speeds, even with particular memory technology, for instance, fast and slow MRAMs have been demonstrated. It also will need to include well-conceived security protocols, particularly if the data doesn't disappear when the power goes off. Now let's look at some of these memories. So we're going to talk about some of these memory candidates. Now there's many emerging memory types vying to replace NOR flash and SRAM. They all share the same attributes. They have a small single element bit cell that promises a scale smaller than current technologies in order to support small, inexpensive die and 3D stacking. They also promise to be easier to use than flash memory by supporting write in place with no need for a block erase, and they have more symmetrical read and write speeds. Finally, they're all non-volatile or persistent. Data doesn't disappear when power is lost, and they can all be used persistent memories. New memories are necessary for Moore's law type scaling to continue. These technologies include ferroelectric RAM, magnetic RAM, resistive RAM, and phase change memory, such as Intel's Optane memory. We compare some important characteristics of conventional memories, that is SRAM, DRAM, NOR flash, and NAND flash, with the new non-volatile memory technologies we just talked about. The higher endurance and performance of MRAM in particular may make it possible to replace SRAM and DRAM if MRAM production volume increases enough so that the price goes down. There we go. Sorry. Now, MRAM is already shipping, but in very low volumes today. Everspin is partnership with Global Foundries, who's building 300mm wafers for Everspin and offers MRAM to other customers for embedded memory applications and system on chips. For example, Everspin's MRAM is used as cache memory in IBM's flash core modules. Another company, Renesas, is shipping an MRAM chip that it inherited through its acquisition of IDT. Avalanche and Honeywell are shipping some MRAM for military and aerospace applications. And other foundries now offer an MRAM option to their system on chip clients, including TSMC and Samsung. Resistive RAM is our third technology. It's also another technology, is also in production, but in a very quiet way. It has been shipped by Adesto, now part of Dialog, since 2013. Dialog, now part of Renesas, was licensing its CB RAM memory technology to Global Foundries to be offered as an embedded non-volatile memory option on its 22 FDX platform and future platforms. ARM announced the spin out of Surfy Labs to develop and license new types of non-volatile memory based on correlated electron materials, or what they call CERAM, and a joint development project with Symmetrix Corporation. Weebit Memory last year announced early production of the resistive RAM devices, which can operate at very high as well as very low temperatures. Other companies currently ship resistive RAM into both commercial and military aerospace applications, and leading foundries are supporting resistive RAM as another alternative to embedded NOR flash. Now, let's finally come to the oldest emerging memory technology, ferroelectric memory, or FRAM. Surprisingly enough, this technology predates the development of the integrated circuit. The photo on this slide, published by Bell Labs in 1955, shows a single SPT crystal with vertical and horizontal metal traces that could be used as a non-volatile memory. From the perspective of unit shipments, ferroelectric memory is also shipped more than all other emerging memory technologies combined, having found its way into over 4 billion chips. It is most commonly used in RFID cards, thanks to its extraordinarily low write energy requirements, which it can do by harvesting energy from the field that interrogates it. Until recently, FRAMs were based on unfriendly materials such as lead and bismuth that most semiconductor fab managers wouldn't want to put into their factories. But in 2011, NAM Lab in Dresden found that a crystalline form of hafnium oxide has strong ferroelectric properties, and that's created new life for ferroelectric memory. Hafnium oxide is commonly used as a high-K dielectric in leading-edge CMOS processes. Fab managers understand how to make it in high volumes. Besides its use in ferroelectric memories, this form of hafnium oxide is being investigated for dynamic random access memory, or DRAM, applications. For instance, researchers have used it to produce a 3D DRAM similar in process to standard 3D NAND flash. Let's look at some applications that are already using some of these emerging memory technologies. This is a block diagram of MBIC's 4th generation Apollo system on chip, which is uses both an application processor and a coprocessor for ultra-low power battery-operated IoT endpoint devices. For instance, it's being used in some Fitbit watches or wearables devices. If you look at the lower left corner, you will see that the system memory subsystem, which is made of MRAM and SRAM. The chip pairs a 2 megabyte MRAM with a 1 megabyte SRAM. MRAM is also being used in Sony's GPS receiver, which can be found in Huawei's GT2 smartwatch. This is built in Samsung's 28 nanometer FD SOI process. This Internet of Things endpoint includes 8 megabits of embedded MRAM. Sony has also shown an MRAM memory buffer with 3 types of MRAM embedded in a 3D stacked imaging device for a camera. There are many other emerging memory devices that ship in production today. This includes an MRAM microcontroller from NXP, a phase change memory-based microcontroller from ST Microelectronics, and ferroelectric RAM-based microcontrollers from Texas Instrument, as well as Fujitsu. Since this RAM will be replaced by new memory technology, then caches will need a new memory. Eventually, even a CPU's registers should migrate, we believe, to new technologies, putting persistence inside of the CPU. That require elements of that SNIA non-volatile memory programming model we showed earlier. Also, fast and slow memories will play side by side to take advantage of the approach that Optane required to mix DRAM and 3D crosspoint. This table shows how this will play out, although the timelines aren't necessarily precise. So if you want to learn more about this, where can you go? Well, it just turns out that my colleague Jim Handy and myself write a report that we've been doing together for several years now. And a lot of this information was drawn from our 2022 report on emerging memories into the next phase. You can find out more information at these links down below. It talks about entire emerging memory ecosystem, the technologies, companies, the market, supporting requirements. 241 pages, 36 tables, and 259 figures. And so with that, though, let's talk about some other things that are going on in the market. In particular, changes in processor design. Let's see how all this ties into new developments in processors. In particular, we're going to talk about chiplets. Chiplets are a way to get past a barrier to continuing Moore's law scaling. Gordon Moore's original paper, he said that there were 3 things that made the number of transistors per chip increase. One is shrinking the process geometries. Another is increase in the die size. The third factor is cleverness. This is an example of that. A die size reached a limit thanks to the way that optical lithography works. There's a maximum reticule size that limits just how large a processor chip can get. All leading edge processors are basically at the maximum size that can fit into the scanner's reticule. To get past this limitation, the industry has decided to put multiple chips in a single package. And that opens up a new opportunity, as these chiplets can be made using different processes. How does this work? Well, here's that same processor flow that we used earlier in the presentation. Once again, there's a logic side of the chip and a memory side of the chip. As long as the memory side uses SRAM, it won't scale with finer processes. It's sure to be great to use another technology, but SRAM is about the only memory you can make in a high-speed CMOS logic process. Instead, you make the processor in a high-speed logic process, and then use another process to build some more economical SRAM, another couple of processors to build a DRAM and some MRAM to give you a very high cache capacity and some persistent cache. You can build either DRAM or MRAM on a logic process, and you can build SRAM cheaper if you don't use a high-speed logic process. This lets you optimize the process for each part of the processor complex. So, but how about the economies of scale? How does that play into this? Well, the deal is that SRAM is made on a processor chip is big and wretchedly expensive. So a chiplet can be pretty expensive and still compete against SRAM built on a processor chip. So here's an example. So the current cost of the SRAM portion of the CPU, as we saw before, is about half the cost of the CPU chip because it takes about half the chip. If the chip costs $200 to produce and half the chip is SRAM, then the SRAM effectively costs $100. Server cache is 64 kilobytes for L1 typically, 1 megabyte for L2, and 1.5 megabyte for L3. Altogether, that's about 2.6 megabytes. SRAM costs would be about $100 divided by 2.6, or about $38 per megabyte in that case. A 4 megabit SRAM chip, that's about a half a megabyte, is currently available and it retails for about $6, or about $12 per megabyte. A DRAM is currently at $3 per gigabyte, or $0.003 per megabyte, 0.03 of a cent. So a memory chiplet can actually reduce the cache's cost, but it can still be orders of magnitude more costly than DRAM and NAND, and eventually even more expensive than a non-volatile memory like MRAM. So costs go down when you use chiplets, even if the chiplet's significantly more costly than volume NAND or DRAM. Part of that's because of the importance of memory and doing computer processes. And so you're going to have persistent cache. I believe that's so. And when you do, the ecosystem already be in place because of technologies that have been developed before. And chiplets are going to accelerate this transition. So, in summary, computing is undergoing significant developments. Memory and storage technologies are playing a major role in making that happen. CXL opens new vistas in a disaggregated and composable data center architecture that includes disaggregating memory. And similarly, NVMe over Fabric allows you to disaggregate and create pools of storage like you do with memory. And these emerging memory technologies are here. They're persistent. They're coming to increasing use in system-on-chip applications. And they're also going to be less expensive, provide new cost options in developing packages that include memory and processing in these chiplet applications. Future processors that will have persistent cache registers, and this whole move to chiplets is going to accelerate the transitions to non-volatile memories, we believe. So with that, I'm open to taking any questions, and I'm going to quit sharing so I can see the questions as they come in. Interesting to see IEC binary prefixes in use, but on hard disk drives and terabytes, not TIB. Yeah, they are given in terabytes, but we have to use some sort of a common comparison for drawing these hierarchy plots. So choosing a terabytes basically is a form we're using for those. Thank you.
I'll ask you a question. I mean, so magnetics have run into the trilemma. They're just down to the point where you can't make it any smaller, and electrons can't be made any smaller. And it seems like the signal to noise limit for memory is about 50 electrons per bit, maybe a few less, 8 domains per bit. Why are these technologies, as they approach the same size or get even smaller, not going to run into the same signal to noise limit?
Well, actually, so the thing that's keeping many of these memories large today is actually the size of the transistor, or the selector for the device. And so, which isn't the memory itself, it's just part of the memory. So getting to smaller transistor sizes with lithography shrinks is helping to make, in addition to reducing the size of the memory itself, is also helping to get to these smaller smaller memory devices. The other thing that can help, of course, if you can get a selector that isn't as large as a transistor. That's what Optane did. They used a diode to do that. The issues are running into on the current memory technologies like SRAM and NOR flash are related not so much to the ultimate limit of just how many electrons you need in order to be able to get good signal to noise. They're limited to technical issues in making these products. And we're not close to that yet with some of these memories, although eventually we're going to run into those limits as well. You know, the basic limits of balancing thermodynamics, you know, how long I can keep data to how easy it is to, how long I can keep data to how fast it is and to the capacity available. And the other thing for some of these memories is the endurance. MRAM has pretty darn good endurance, but some of these other memories can wear out, like the phase change memory that used in Optane would eventually wear.
Yeah, but I mean, if the phase change, so many phase domains per bit. If you can get down to one, fine, and that's, you know, that's it. But maybe you can't. That's the issue in magnetics. And I think you may be mistaken about DRAM, about SDRAM and flash in terms of electrons per bit. But so far,
DRAM scaling is slowed too, right?
That's different.
Yeah, and that's it's slowed down. It used to be about 40% per year. Now it's 12% or even less per year. You know, in terms of the density increases of DRAM. All these technologies have gotten harder, partly because they're approaching ultimate physical limits, but also because the processes to make these things are getting harder. For instance, the really fine lithography products are being made with extreme ultraviolet lithography. These machines are hugely expensive, and the next generation, the high numerical aperture EUV devices are going to be even larger and more expensive. So, you know, there's physical challenge, fundamental physical limits that we're dealing with, but also the costs of making parts and the processes you have to go to make things smaller and to get more of them onto a given package.
Thanks, Tom.
Oh, you're welcome.
I have a different question. Tom, you will be the IEEE president. Is it elected or just president for this year?
I'm the president-elect. I'm still on training wheels.
Okay, so do you have any perspective for the IEEE activity?
There's several things that I think are important that we work on. So Seifer Rahman, who is the president this year, has a very significant focus on climate change and technologies to help to deal with climate change, mitigate it, or to reduce it, as well as the general sustainability technologies. And that's an important goal. It's something that I also can support. But there's some things that I want to work on, and actually that were important in my campaign. One of which is attracting and retaining our younger members. The average age of IEEE members in the US is increasing. It's about 55 now, and worldwide it's in the 40s. And we do attract a lot of students and young professionals, but we also lose them at pretty high rates. And so we're tending to get older over time. If we're going to remain relevant, we need to do something about it. So one of my goals is to see what we can do about engaging with younger members, letting them know what IEEE is more than a student club for the students, but also finding out what it is that will attract and make them want to be part, being part of a professional engineering organization, part of their career. So that's one of the things I think is important. Another is how can we create, and I think it's actually related to the first one, how can we create greater value for people, technologists working in industry, and for the companies they work for? And I want us to take find new ways in which we can engage with people who are working on the practical application of technology, not just researchers, and help them to be successful, as well as do more things that can have make companies want their employees to be members, for example. A third thing is I think we need to be doing more to get information out about the IEEE to the outside world, and so that they know what IEEE is, and the value it shares, and also about the value of members of the IEEE, that they are professional technologists, so things I'm thinking of doing there. One of which, when I was IEEE USA president back in 2019, we got a program going to create professional videos called IEEE's My Competitive Edge that have actually aired on cable television stations throughout the United States. I think it actually was part of the reason why the retention rates of IEEE members in the US increased last year, and we lost fewer people than we have tended to lose as IEEE members in the US last year than we had in prior years. I think it was part of it. And I'd like to see us doing more things like that, talking to world leaders, to policymakers, corporate heads, and even beyond, the CTOs, about what IEEE is, what all we do, and about the value of our members and of IEEE as a whole. By the way, some interesting facts found out is there's 21 members of the IEEE have won Nobel prizes so far. Another interesting statistic is last year, 140,000 patents were submitted by IEEE members in our 400. Actually, the latest number I heard, that's going to drop real soon, over 440,000 IEEE members, at least until the February termination of those that didn't renew happened. So apparently it's the largest number that have ever been IEEE members at that point in time. So those are some of the things I'd like. I'm supporting what Cypher's doing. I want to reach out to younger folks, want to have better engagement with industry. I want to create a better visibility for the IEEE and for IEEE members. Again, another reason why people might want to be members. And I support Cypher and his activities. And another thing as president is that I'm hoping that I can create, working with, when I'm president, working with the past president who will be Cypher at that time, and whoever's elected this year, to try to create an IEEE that create programs that can continue. It's really hard to get everything you want to do done in 1 year. If you can work with adjacent presidents, might help you in creating a longer term impact, and be able to coordinate on the things that you want to do in your term, and make sure they get done by not just being you working on it, but the past president and the future president working on it as well. So those are a bit about things that I'm looking at as IEEE president. It's going to involve a lot of travel. It's involving chairing the IEEE board meetings, but it's also fun for me, at least, to be able to talk to our IEEE members. And so Min and Tom, I'm really glad that you folks invited me to come join you and speak to you today, and talk to you a bit about things that interest me, in the storage and memory world.
Thank you, everybody, for your participation. We will hosting more talks throughout the year. Please stay tuned.